Now we'll talk about intake, not the manifold but intake pipe, on how it works and what it does, and of course certain designs that work better than the other. And of course in this video you will find out or figure out an idea that works for you as it did for us. We'll delve into the design function, physics, and the behavior of air as it expands or the pressure changes. Some dyno examples and even race functions that's used in Formula 1 and everything else. So you know you'll like this. Alright, as we all know, when air travels towards a divergent zone, it expands. And as it expands, it loses airspeed. So it becomes higher pressure, you know. This is why on weather reports, the weatherman talks about low pressure zones or low pressure areas. That means the airspeed is high in that spot or area, you know. So that's a windy place. You better get your windbreakers ready. And my other homie, Daniel Bernoulli, the guy behind Bernoulli's principle. You can see on this diagram how the pressure goes higher as wind or air goes slower, right? You can see in this equation, it is an interesting phenomena that you can take advantage of when you know what you're doing. This is the basic function of a NACA duct. It pulls air and then suddenly expands it slowly to turn it into a high pressure air. NACA stands for National Advisory Committee for Aeronautics. Then it changed to NASA, so they probably know what they're talking about or doing. The NACA duct is more common, as you can see, in the Porsche GT3, even on the JDM Skyline. And you can see here on my favorite, the Ferrari F40, you can see it's clearly visible. And Nick is gonna go crazy for this. Nick has a channel called Autotechnic. He's been a Ferrari and BMW master technician for 20 years. He actually got an award for the best Ferrari master technician in the world. So, you know, it's gonna be interesting because he knows more about this than I do. The interesting part is that he has a B18 that has a Skunk 2 Pro 3, and he actually tuned it to idle really smooth down to 900 RPMs. So when you think about it, when you know your stuff, you know your stuff. Now that we know that air slows down as we expand it and it increases pressure, look at this. Something that you've never thought about, but hey, even the planes, the aerofoil of the wing is acting as we were talking about to create lift. The airflow above has to travel faster so that it meets the bottom part at the same time. Therefore, the top becomes low pressure because it's high airspeed, and the bottom is low speed so it increases pressure. Therefore, it produces lift and goes flying. Got it? Now going back to expanding air and increasing pressure. That is the design theory or purpose of our design of the intake. Look at this. Well, we know the entry of the intake pipe is where you put the velocity stack because that's the entry. That's true and that makes sense. But when you think about it, isn't the throttle also the inlet of the plenum? So it's filling the plenum. So this is what we did. You put a radius entry before the throttle or right at the entry of the throttle. This way it fills the plenum even better or even more efficient. And you slowly expand or do a divergent chamber before the velocity stack. This way it becomes high pressure air, you know? And that's the goal of this design. And of course, you're still gonna add length to the intake for the Helmholtz resonator, which we'll talk about a little later. The conceptualization of this idea or of this intake was between Les Shock of one cam only and me, and also Glennis of dcvs.org. They got to do their own stuff called TBRIA, which is throttle body radius inlet adapter, which is pretty cool and all that. It's just that I don't have the machining capabilities that they had, so I did this. And I say this because, just so you know, by now, if the locals here start doing this, well, you know who's the copycat, right? And I'm not worried, because by doing that, it ensures that their in-depth knowledge on this is inadequate. A few images to emphasize on what we're talking about. Notice the intake. It expands at the last minute right where the velocity stacks or the trumpets are. This way, it takes in high pressure air for better efficiency, which means more performance. Now, with that explained, now we talk about the intake pipe length of a short ram and a cold air intake. A short ram is about 14 to 15 inches long. However, a cold air intake is about 32 to 34 inches long. And when you think about it, due to a lot of misconceptions, the cold air in the cold air intake is of less effect. What's really happening is the length of the intake pipe, the resonance tuning or the resonance effect is creating the increase in power at certain RPMs. It's called Helmholtz resonator. And here's the dyno sheet that you can see. At this part, between 4.5 and 5,000, you can see the hump in power. Even here, that's from the cold air resonance. However, on the top end, you can see this part. It's also because of the stacking of air. Because when you think about it, as air gets into the valves, into the port, the piston goes up with trying to compress. Instead of having a reversion by blowing it back out, the length of the intake pipe is stacking back a lot of air behind it. So it's getting actually pressurized. This is what increases volumetric efficiency. And that is why on the dyno, when you put a velocity stack and a long extension, it makes more power. And also locally, that's why when they have a ram air, they think it's faster at first gear and second gear, but that's not because of the ram air. It's because of the length. Because you're nowhere near the speed where you can take advantage of the aerodynamics. So it's just the length. As I talked to my good friend Al Franklin, the originator of this one-up pistons and owner of Frank's Motorsports, he said locally that we are in a dire need of a proper intake system with an airbox, that is with filter or with air filter, because we have so many locals that run their intake with just a velocity stack for every day, and causes extreme wear, you know. So hopefully this works really good, because this is the only thing or the only design that we're willing to offer in the market, not the other intake. The short ram is about 14 to 15 inches long, and the cold air intake is about 32 to 34 inches long. So we did this. Laying out the pipe like this gives us about 30 inches long of intake pipe length. So it's not really as long as a cold air intake, just a few inches short, but it's still double a short ram intake length. So it's still gonna be world better than a short ram intake. And the airbox will be right there where the factory is, and it's gonna run a flat panel filter so that it's very efficient. And of course, the end of the pipe, the intake pipe, will have a velocity stack that will be radiused well, and it's gonna be an elliptical shape, so it's gonna be really good. And this is how it's gonna be on an EG engine bay. See, if the airbox will be at the same place as on the EK, and at the opening of the intake pipe is the velocity stack before the panel filter. This way it's performing efficiently. There. I already got a template for the EG because my daily driver is an EG, and also for an EK. So it's just fabrication that's needed to be done. But of course, we're gonna be testing it over and over, because you know us, we love research and development. Now, going back to Bernoulli's principle, as we know, as you diverge air into an expansion, it raises pressure. which is really good for the engine's induction system because the higher pressure air is a lot more dense. As you can see here, the expansion goes at the last minute. This way it's good and efficient. However, this is also excellent for heat exchanger, which is a radiator or even an intercooler. Look at this. Notice the inlet. It gradually expands towards the heat exchanger or radiator, increasing the pressure. Even on the Caterham Formula 1, look, it expands slowly to be high pressure. Now that's efficient without causing any drag, or at least not a lot of drag, and taking advantage of the speed. Need more? Look, a perfect example of Bernoulli's principle. Look, it expands all the way to the radiator to be more efficient. And it's funny, right? We got local turbo express that runs, let's say when you run a 1000 horsepower rated intercooler. That is correct, if only the inlet and the outlet of the air is sufficient, because if not, then it's not rated for that much. It's actually below par, you know, and people wonder why they can't make what they were expecting, you know. It's that simple. So with that said, I came up with this design, and it's not because I need more cooling, it's just I want it to be more efficient. And look, this could be in place for the radiator or the condenser, you know, just to make it even more efficient than it is. And achieving that would let me block off all the other openings and make it more aerodynamically efficient. Now here's for the better visual. You can see it's taking air from the bumper grill all the way to the radiator or condenser. Or you can move the inlet upwards near the plate number. This way you can shut off the whole bumper grill. It's gonna be more slick. Now going back to the earlier intake with the taking advantage of Bernoulli's principle, it takes a gradual expansion. This way you raise the pressure before the inlet. This is the version 2, and you can see here, you can see the stack inside, and this is designed actually to increase the extension length. So, you know, even though we haven't tested it, we already have a version 2, and that's the beauty of research and development. You can have 1 or 2 different things that you can test on, because we all know it never goes as it planned on the drawing board versus reality. And definitely one of this is gonna do wonders, right? Now if you enjoyed this, hit the like button, will ya? This helps spread the video to a lot more people so they can enjoy this. And you can click here if you want to check more stuff and subscribe.